Morning.
Todd, are you with us?
He stepped out
Matt?
for a second.
Okay, no problem, as long as he's there, in the near neighborhood. I think we have all of our technical things worked out up here in Idaho Falls, so let's get started. We have lots of good stuff to cover today. I know I introduced myself to the folks here in Idaho Falls before, and I introduced myself to the whole group, I guess that was last week or the week before. But let me do that again. I'm Dr. Mary Lou Dunzik-Gauger, and I am a professor of nuclear engineering here at Idaho State. I also have a joint appointment, which means I spend part of my time with the Idaho National Lab. It turns out it's a 50-50 joint appointment. So I'm truly schizophrenic on a given day. I run back and forth. But that's all right. I get the best of both worlds that way. Today, I want to talk to you about radiation basics. It's the best thing to teach. It's a lot of fun. You get to play with toys. We're going to do some demonstration stuff here, and in Pocatello, Todd will do some as well. And then we're going to have actually collect some data today that will give you a homework assignment. So let's start. Just really quickly, I want to take a look quickly at just the big picture sorry, I'm getting all tangled up here. The big picture of radiation science, radiation discovery, and then talk more about what is radiation, the types of it, the characteristics, the sources of the radiation, and then certain concepts that are unique to radiation, radioactivity of species, the half-life, and effects of shielding and distance. All right, here's the first slide. This is our big picture slide. Now, this is what most people think of when they think of science. It's crusty old guys wearing lab coats, and it's really boring. Well, that's not why I put it up here. Why I put it up here is because I want you to take a look at that first date up in the left-hand corner. 1895, is it? 1895, when Wilhelm Röntgen discovered X-rays. Now, that's just a little over 100 years ago. All right? Now, of course, you guys can't relate to 100 years. I can't relate to 100 years. But, you know, maybe that's your grandparents' or great-grandparents' age. It's not really that long ago in the big scheme of things. That was the first inkling that people ever had that there was such a thing as radiation. That was one of the first inklings of the atomic structure and what's in it and what comes out of it. That was just a little over 100 years ago. Now, if you think about that, then you must realize that we are here in the infancy of nuclear science. Look at what we've done, right? We've made nuclear reactors that power the world. We apply radiation to so many different things. And we're just starting. I think that is the most exciting thing about this field. It's not necessarily anything I do on a day-to-day basis. It's, which I like as well, but it's more the excitement of the potential for this science. And if you leave with nothing else out of this whole nuclear exposure, I hope you take that with you, because it is an incredible science. It's powerful, and it really has so much more to offer as we figure it out. So, real basic now, and forgive me if you think I'm talking down to you, because I don't mean to. I just want to put it in real simple terms and get to the good stuff. Really simply, radiation is the transmission of energy, and that energy is transmitted either via particles or via waves, one of those two. But there are different flavors of radiation, and usually when you hear radiation in the context of nuclear, what people mean is the kind on the right, ionizing radiation. Because things like radio waves and ultraviolet light, they're radiation too. That's energy traveling in a wave, but it's not the kind that you associate with nuclear. Those kinds are usually what you see on the right. Alpha, beta, gamma, X-rays, and neutrons are very common ones. And it's called ionizing because it ionizes atoms. One thing I'm sure you'll learn if you haven't already is engineers are not really creative about naming things. So ionizing radiation creates ions. Okay? This kicks out electrons, and that's a property that it has. Those other types, ultraviolet and microwaves and so on, they don't have enough energy to do that. So they're not ionizing radiation. Now, I'm sure you've seen this before, but you know from probably you had one of these in a high school classroom in your science teacher class. But the main difference between those types of radiation is just the wavelength. And the smaller the wavelength, the more energy that comes. So to the left there, at the very, very small wavelengths, with X-rays and gamma rays, you have enough energy to ionize the ions. Where does radiation come from? Well, if you go to a doctor's office to get an X-ray, that comes from a machine. You can actually make certain types of radiation with some clever instrumentation. But most of the radiation that we're familiar with in our natural world comes straight from atoms. And those atoms are considered radioactive or unstable. And what part of atoms? Well, that would be the nucleus. Again, not creative about naming things. This energy comes from the nucleus of the atom, therefore it's nuclear engineering or nuclear medicine. Now, what is radioactivity? What makes an atom radioactive? Well, something about it is not stable. And in order to become stable, it sort of rearranges itself, and in the process will give out part of its nucleus. It'll give out energy, it'll give out little chunks of matter, or both. And that stuff that comes out is the radiation we're talking about. It's very energetic radiation because the nucleus is a very energetic chunk of matter. I know you've probably had exposure to just the general structure of the atom for as long back as you can remember in school, probably since middle school with the nucleus and the electrons and so on. But a perspective you might want to consider when it comes to the atomic structure is the fact that the vast majority of the mass of an atom is in a nucleus. And an analogy I've heard that kind of speaks to me is if you were to assume that the size of an atom were about the size of a football stadium, then you could take a green pea, and walk onto the 50-yard line, set it down in the middle of that 50-yard line, and then start walking to the bleachers. And then you keep on walking to the very top bleacher. And right around there is where you find about the first electron. Now back up a minute. The vast majority of the mass is in that pea. And what's more, everything in that pea is repelling each other. It's all positive or neutral. Think about the amount of energy to hold that thing together. Pretty amazing quantities of energy. And that's the energy, part of which you release in these mechanisms of radioactive decay. One thing I learned when I came to live in Idaho was how to say, "you betcha." And that's the best answer for this question. If radiation comes from everywhere and we're made of atoms, we're everywhere, is there radiation around us right now? You betcha. That's background radiation. Here is just sort of an average overlook at an American's background radiation dose. Now I say background, but there are actually medical procedures in there. So it depends on how you define background. But the average dose of an American looks like that. The units come out to about 360 millirems per year. We'll talk about what that really means in just a minute. But the vast majority of it comes from the earth. It comes from the rock and the soil and the radon gas that's released from the rock and the soil. It's just part of our natural world. After that, we've got a good bit of cosmic radiation, which is a good thing. If we didn't get cosmic radiation, we wouldn't be alive. We need the energy from the sun. Medical is significant, and of course that varies from individual to individual. You see that nuclear power is a very, very small quantity. It helps to get that perspective. This is just another look at the same idea, but slightly different way of breaking it down. There's a separate category for just radon gas, and then other natural sources is in the blue. Man-made, other than medical, is in that sort of orangey color. And then again, the amount from anything relative to the nuclear fuel cycle or fallout is so small you can barely see it.
I have a question real quick.
Sure.
So if we can make energy out of splitting an atom and having the instability give off energy, right? Couldn't we technically use our own bodies, which are creating cells and creating its own matter from smaller, from like plants and whatnot? Couldn't we use like just small cells from our own body to create energy?
I'm not a biologist, but I see one comment. If we could go to the Elmo, it's pretty much an energy balance question. In order to make cells, you have to eat. So you take in fuel and you put out heat and kinetic energy. Yeah, you make cells when you're growing. You make cells to replace your dead skin cells, all that kind of stuff. But it's a fueled process, and it's what keeps you alive. You need to give fuel to have the action go on. What we're talking about is releasing a sort of kinetic, or a potential energy in the nuclei of atoms. So we have to add, in the case of the fission of uranium-235, a neutron that is just literally a room temperature neutron, and we fission that into what are called fission products, so 2 fission products, and some more neutrons, 2 or 3 neutrons, and a lot of heat energy. The amount of energy that's released from here is on the order of mega electron volts, million electron volts. The amount of energy released in a chemical reaction, which is what cells do, is on the order of electron volts. There's a million more times energy from one atom that you can cause to react in a nuclear way. So I think that's probably the best answer I can give you, but think more about that and think of the input and the output. It's an energy balance question. What do you put in and what do you get out? Okay, back to the slides. A quick look at the units of dose and exposure to radiation, because I mentioned that the average dose was 360 millirem. A rem is defined, now you have to understand that these things were defined over time in a manner that reflected what was known at the time, like anything is defined. A rem is a Röntgen equivalent man. I'm sure you understand where the term Röntgen came. But you back up a little bit. A Röntgen is a unit of exposure, and it was defined by the way they could really see radiation at the time. It was defined by having a volume of air and ionizing it, knowing that it was ionized because of a current that was produced, and having it ionized by X-rays or gamma rays. So you go from ionizing air, and then you want to apply a dose or an exposure unit to people, and they had to kind of consider different things. A rad is still used, a radiation absorbed dose, and that's the energy actually deposited into a material. But most important to people is the rem, because the rem takes into account not only that you've absorbed the radiation, but the effect that that irradiation has. because not all radiation is created equal in terms of the effect that it has on your body. So the REM takes into account the type of radiation. I think, let me see, I have some numbers next to give you. Sorry, I'm having problems jumping ahead here. I wanted to jump to a slide that shows some number values. Again, look at the units, dose in REM. From 0 to 25 REM, there's no observable change in people. Now, I said the average dose was 360 millirem, right? So we're talking 0 to 25,000 millirem here. There's no observable effect. And people get exposed to huge range of natural doses depending on where they live, how often they fly, how many medical procedures they have. It's just part of our world. It's not until you get to 25 to 100 rem, or 25,000 to 100,000 millirem, that you see any slight changes in your blood. And you have to get some serious exposure, 200 to 600 rem, where you see a significant chance of death, for example. It's really hard to get that much dosage. In fact, I'm not even sure I could figure out how to do it, short of trying to break into a commercial reactor and pry open the reactor vessel and jump in, and that's just not an easy thing to do. So it's difficult to get that kind of exposure.
Sorry, so on that note, does exposure last? Like, can you get a little bit of exposure and then get more later, and then by the time you're like 85, you have 3,000 so much exposure?
That's a very good question. If my slides weren't being so obnoxiously slow, I'll give you a quick answer, and then there's a slide later that I'm not going to try to get to right now, seeing how slow it is. But the answer is no, you do not accumulate dose. Unlike, for example, a chemical poison like mercury that sort of builds up in your system over time. You get exposed to radiation, and your body does whatever it does with it, and you know, you go away. There's something called an acute dose, whereas if you get a lot of radiation at one time, then you can get so much that the effects of the radiation cannot be counteracted by your body. But if you have that same amount of radiation that's in the acute dose, but spread it over a long period of time, it's a completely different effect. It's sort of like aspirin. Some people take a couple of aspirin every day for their blood pressure, right? And it's a very good thing. Aspirin's a wonderful drug. But if you take a whole bottle, you die. Okay? So you have a different reaction in your body to the different quantities. So no, you don't build it up.
I know I'm probably getting annoying, but just one more question. When it comes to like medically and you get radiation to get rid of cancer, could you kind of give us an idea of how many REMs are in that, so we kind of know like what exactly you can use on the human body and what it does?
I'm not a medical expert. And off the top of my head, I know that you can get what I'll call huge doses in medical procedures, but in most medical procedures, those doses are focused at a tumor. They're focused in one area. It's not a whole body dose that affects all of your systems. It's focused at the bad cells. Now, if you do get something that's meant to go through your entire body, then of course it would have to be less. Actual number values, you know, you can look those up on the internet. I really don't know off the top of my head. But I'm thinking on the order of REM, certainly, depending on the type of therapy you're talking about. Now that kind of takes us into this next slide, because different types of radiation are also used for different things. medical is a great example. You know that you can use x-rays to image things in your body. They go through the soft tissue, they get stopped by the bone, and make a picture on the other side of you, right? So they have that certain energy value that you can use. Gamma rays wouldn't be good for x-rays because they go straight through everything and you each have this big blob on the x-ray film. That would not be very effective. But that makes gamma rays really good for applications where you need the radiation to go the whole way through. Gamma is just a wave. There's no particle there. It's purely wave energy. Beta is a negatively charged particle. It's very, very small, just like an electron. If you met one, someday, you wouldn't be able to tell it apart really from an electron, except that it wouldn't necessarily be hanging out with an atom. Alpha is the most massive of radiation. It's got 4 subatomic particles, 2 neutrons, 2 protons. It's positively charged, 2 positive charged, so it is most massive and most charged. And again, that has implications for how you might use it. The slide didn't bring through all the information we need to see here, but we'll wing it. Because of the difference in nature of these types of radiation, it would stand to reason you're going to have different penetration abilities. Now, I just told you gamma is going to go through everything. So you would expect down here at the wave part, the gamma is going to go the whole way through this block of whatever it is. And that's the case. Why is that? Well, there's nothing really to slow it down. There are no particles that bump into other things. There's no charge to attract it to a local atom. And so it just goes through and eventually all of its energy dissipates and the wave dies out. The beta just above it is charged, is a particle. So it will go in for a certain distance. It's going to get banged around as it gets repulsed by the electrons of atoms. And eventually it'll get sucked in and become part of an atom. The alpha is going to go the least distance because it's most charged and most massive. In fact, I have some sources here to demonstrate just that. If we could go back to the Elmo, please. I have here sources of alpha, beta, and gamma radiation, and I'm sure it's not terribly easy to see what it says on them, but I can read it for you. The alpha source is the isotope polonium-210. The activity that's in this source is 0.1 microcurie. Curie is a unit of activity. It gives a half-life there of 138 days. Beta is strontium-90, 0.1 microcurie as well. Its half-life is almost 30 years. And my gamma source, cobalt-60, has a half-life of almost 30 years as well. I'm sorry, no, I'm thinking of cesium. This one is 5.27 years. And this one's 1 microcurie. I brought along today my rusty, trusty Geiger counter. And I'm going to demonstrate what I just told you about their penetrating ability. So first, let's listen to what the alpha source sounds like. Hopefully you can hear the beeps. This thing kind of comes and goes in its ability to beep very well. So I'll hold it up to my microphone so you folks in Socotel can hear it. And what I'm going to do is bring the source progressively closer to the counter. Now I'm taking it away. Boy, it doesn't take long for it to die down, does it? In fact, alpha only has a range of about 2 to 3 centimeters in air. It can't even go very far in air. It can't get through your skin. It can't even get through a sheet of paper. Listen to this, okay? Here is alpha sitting straight on the detector. I'm about ready for a new source, I think. This one sounds pretty pitiful. And here again. Boy, it sounds like there's still a lot getting through there. The alphas don't penetrate paper. When you keep hearing blips like that, you're hearing things like cosmic radiation coming through, maybe something from one of my other sources. But alphas are too big to get through paper, so it's very easy to shield them. On the other hand, alphas are very, because they're so massive and energetic, they can do serious damage if they get inside of you. So if you happen to, something comes over you and you swallow an alpha source, you're going to have a lot of energy deposited directly to one of your internal organs. So it's always best not to swallow alpha sources if you can avoid it. Okay, here's my beta source. I'm bringing it closer now. Okay, I've pegged the needle on that one. I'm going to change to the ×10 setting. This one kind of croaks. Let's try paper really quickly. I know this is kind of awkward to see in Pocatello, but the more important thing is to listen. So I think there's a difference. What do you think? Okay, here's with the paper. Here's without the paper. So some was shielded, but certainly not all. Here's a sheet of just a plastic, about 1/4 inch thick. Let's try that. Significant reduction. And I think we might find that if we took some background counts over a period of time and compared it, we might have stopped just about all of the beta coming through there. So beta is not that tough to stop either. It can get into the top layer of your skin, but not very deep. And finally, we'll take a look at our gamma source, cobalt 60. Again, I'll bring it closer to the counter and let you listen as I approach. A little hard to stay lined up because the active point that I want to focus on is this bit right here. And so as I pull the source away, I'm not sure I'm exactly lined up quite right. But you can hear, I think, more gammas at a greater distance than you did the alphas and betas because it has a longer range. Okay, so we'll listen to this by itself. Let's listen with paper. Let's listen with the plastic. Opinion on that? Is there any difference? A little bit? Some people say yes. It's really hard to tell with all these clicks. There might be a little difference, a little bit of shielding, but keep in mind that every time we add a shield here, you're also adding distance. So you have two effects going on. I also happen to have my rusty, trusty piece of stainless steel. You should see the TSA guys when I bring this on the airplane with me. They go ballistic. You know, they don't care about my sources or my Geiger counter. They get really upset about the stainless steel. I have no idea. Okay, so again, lining up might be a bit of a challenge. I'm going to put the source on one side and the counter on the other. Clearly there's still some getting through, but we've also added an inch of distance which is also a factor. Turns out you need about 3 or 4 inches of lead to effectively stop gamma, something very dense. The denser you get, the less thickness you need to stop it, right? So with uranium, you'd need a heck of a lot less because it's much denser than lead, for example. Or the way they do in facilities that work with radioactive material, you can have something on the order of 4 or 5 feet of concrete, and that will shield you from radiation as well. So back to the slides, please. So here's in summary of what I just said. You can stop the alpha with paper. The beta you can stop with wood, concrete, lead. And the gamma you can stop with lead and concrete if you have the right thickness. When you go to get a dental x-ray, I'm sure that you've been subject to the lead apron that they put on you, right? Lead's a good shield. That's why they use it. Okay, we'll speed through these next few slides so that we can get to the demonstration that Todd's going to do for us. Just really quickly, I wanted to give you a feel for how we can apply the properties of the radiation. Alpha, because it's very highly ionized, is used often to remove static charge. For example, you can find alpha sources in a lot of copy machines. So the paper will run over the alpha source to remove the static charge, which, if you think about it for a minute, is brilliant. Because think about all of the pages in a Xerox machine getting stuck together and what chaos that would make in your copy machine. So that's one application. There are many others. Beta is often used for thickness gauging. Anything you can make in a sheet and you have to roll up in a roll of paper, aluminum foil, other things escape me right now, but similar things. You can have a beta source on one side, a detector on the other, and you can know exactly the reading you need if the thickness in your material is correct. And if what you read in that detector changes, then you know, okay, there's something wrong with the process, stop the press, we need to adjust the thickness. Gamma radiation is used very effectively for food irradiation. The green leafy symbol there on the right is called the radura, and it's an international symbol for food irradiation. And you just see 2 example pictures there of potatoes on top on the left were not irradiated, on the right were. And on the left, strawberries that were not irradiated on the right were. And the irradiation does not stay behind. It doesn't create some odd entities inside the food. It simply deposits the energy to kill the bacteria, for example, in the food. Just the way any sort of cooking would do. We'll skip over this in the essence of time. I mentioned the unit of Curie on my sources, and Curie is actually a unit that talks about how many disintegrations per second. In other words, how many bits of radiation are coming out per second from an atom. Very quickly here, why are we concerned about radiation? Well, I think it all boils down to the fact that we said radiation ionizes atoms. Well, we're made of atoms, aren't we? Our cells are made of atoms. So if radiation comes into a cell in our body, forms ions, one of several things could happen. We could have no change in that cell or a neutral change. That cell could die, and then the body would replace it or not replace it. You know, cells die in your body all the time. That's a natural process. Or you could have a change in cell that is not a neutral change. And if that cell reproduces, then you get what's called a cancer. Now that cancer could be a benign cancer or a malignant cancer. Causes of cancer, as I'm sure you know, are quite wide and varied. But it is true that radiation can cause cancer. It's also true that radiation regularly cures cancer. Right, my last slide. How do we protect ourselves? It's very simple. And if you ever take sort of radiation training at a workplace, you'll get this kind of hammered into you. Time, distance, and shielding. You put something between you and the source to stop the radiation. That's kind of a no-brainer. You keep your distance from it. We saw that as we moved those sources away from the counter, the dose really quickly went down. And you limit the time. So that's back to the question we had before. You can get a lot of radiation dose if you spread it out over a long period of time, because your body just says, oh, no problem, I'll fix that cell, and you go on. Okay? All right. Todd is going to talk about, oh, that's the best slide. Todd is going to talk about more about the radiation distance from the detector. Keep in mind that we're talking about something we consider a point source. And if you go out in all directions from that point, you're really diluting the amount of radiation that you're going to see if you're on the surface of that sphere outside the source. So the radiation intensity decreases greatly with R. Over to you, Todd.
Okay, is this mic on? Can you guys hear me? All right. I've got a couple little things. We're not going to have time to go through them. But if anybody down here wants to stop after, please come up. We can play with some of these meters and some of these sources. If they kick us out of here, we'll find somewhere else to go. Spend an hour if you guys want, and we can go through and demonstrate this stuff if anybody has an interest. Same for the people in the other room here. We thought we'd give you some kind of assignment or something to do. And so we're going to have to go through this a little quickly. As Mary Lou said, these radiation drops off quickly with distance away from the source. So we're going to look at something that's really only applicable for a point source and do a little experiment. One of the things you're going to have to do throughout your engineering career is write lab reports, and they're kind of painful. So I propose for this assignment you guys write a mini lab report. I don't want you to do a lot of writing. What I want you to do is have basically describe the experiment, describe the theory, what you're trying to look for. Plot this data out that we're going to take. Do a little analysis on it and write your conclusions. Why or why not it doesn't match the theory. So we're not looking for a lot. I'm not looking for anything in a very formal format. I would say a plot on one page and maybe a page of text, a few paragraphs. So if you have any questions, come talk to us. As Mary Lou said, that these sources will drop off, or as Dr. Gauger said, these sources will drop off as a function of distance. So let's say I have a source here that is a point. And that source has some kind of strength of S particles per second. That's just some number of particles per second in curies or whatever. So units of 1/seconds. If I were to look at what the flux would be, or how much I would see coming through a surface of a sphere at some distance away, then that would be this particle source strength with units of 1/seconds divided by the area of that sphere. Anybody remember what the area of a sphere is? 4/3 pi r cubed, or r squared? 4 pi r squared. Thanks, Jay. 4/3 pi r cubed is the volume. So 4 pi r squared. Now if I had some detector of a given area that I was going to measure the amount of particles that hit, that detector would have some area A, which would have units of area squared. So this would give me the count rate, which is going to vary as 1/r squared. All the rest of this is a constant. So what does that mean? It means that if something is small enough to be approximated at a point, if I move my detector and double the distance, or if I double the distance I'm away from a source, the amount of radiation hitting me goes down by a factor of 4. So every time I double the distance, it goes down by a factor of 4. Now that's the same for any kind of radiation from a point source. That's the same for light from the sun. You can't go out to the outer planets and expect to use solar power, because every time you double this distance, you have 1/4 of the amount left. So things to look at. A couple of things you may not be surprised about. I bought a little thing of new salt, which is actually it's actually potassium chloride instead of sodium. And potassium 40 is radioactive, so there's some activity in this. Another thing you can come up and play with later, in the 50s they used to have something called Fiesta ware. And this was actually colored with uranium. And they're actually pretty hot for a dinner plate. Nobody here will self-heat your food, unfortunately. I thought we'd do an experiment with something very common, or at least it used to be. And these are just mantles for a lantern. You've probably all seen these. About the mid-90s, they stopped producing these with thorium. But the old ones have thorium in. The other day, I was over here in a friend's garage, and he had them hanging up. And so I convinced him they were a health hazard and took them. They're kind of hard to come by these days, and they're a nice calibration source because they have the thorium. So one of the things I thought we could try, and maybe I can get a couple of volunteers up to take this data. Come on, a couple of you guys come up here. We don't have much time. Come on. I won't bite. Because I thought what we would do was take one of these meters, hook it up to it, put these mantles down below, and then just vary the distance. And take some data of the count rate versus the distance you're away. Now we can't get too carried away because this mantle isn't that hot of a source. And if we get too far away, we won't see it. So I was playing with this a little bit more the other day. I got about 18 inches out of it. We can obviously get higher than this. The other thing we have is this meter is going to vary around a little bit.
They could switch to the Elmo here, and I can be writing the data down as you take the numbers. Would that be helpful?
Sure. Looks like we can see, if you hold this for just a second, looks like we can see about 20 inches. So we'll see if we're lined up here. We'll try to make some quick guesstimates, and there's going to be lots of error there. Because obviously this isn't a point source, right? That mantle's got some volume to it. And I don't have a very good instrumentation to read it with. So the needle's moving like mad, I'm kind of trying to take an average. So let's climb up 20 inches and 180 counts per minute. So hold that, keep holding that. No. It's just, this is counting the number of times that the photons hit that detector. So that's number of particles that hit. Yes, sir?
And what is this for? Well, so which item are we using?
This is for a package of mantle lanterns. Lantern mantles. Why do I always say it backwards? Let's go down to 18 inches. Pull that a little closer to my detector, will you? We'll just do it every 2 inches and call it good. That's about, it's not quite 18. Let's call that about 19, 100, yeah, there were 180, 190. That was 18 inches. Let's go down to 16. That's about 2,200. Let's go down to 14. Good catch. That was, yeah, it was 220. I was on the 0.1 scale. Now on the 1x scale at 14 inches, and I'm reading about 375.
In Idaho Falls, that was, 220.
No. At 12 inches, and I'm reading about 350. You can see how hard this is to read. Been better off just to hold it handheld. That's 10 inches. Actually, let me change that because my geometry's changing. That's about 300.
Let me give you a feel for what he's trying to deal with. Take a look at this dial. Mine is not as sensitive as his, but when well, I guess I ought to turn it on first. When I'm sorry, I was just showing them. Oh, it's not going to cooperate. Oh, see how it bounces around? But I'm not changing the distance from the source. So that's what Todd's dealing with, trying to come up with an average as the needle bounces around.
Okay, this one at 8 inches is running about 850. Yes. 6 inches. Call that 1125. At 4 inches, 2200. We're really starting to run on our point source approximation now. About 2 inches is running 6,000. Nah, no need getting any closer, but you can see it really starts to pick up. If I were to get back to the end and repeat the experiment Mary Lou just showed, and show you how much this one is. Come on. See, that's how much meter movement I've got, so I'm trying to average between it. So there's plenty of error there. Take that data and plot it out. It should fall out a 1 over r squared plot. If it were me, I'd either try to do a curve fit. I know Ken did some experiments with you and had you plot a little data, so you should be used to that. If you need help, come find one of us. All of us will be more than happy to sit down and help you analyze this.
Can you post that data on the Moodle?
I suppose we could. I never have used Moodle, so one of us can post that data. It's not very much. You can pass it around too, because it was only a few points.
So basically, you just want us to describe what we did and then just graph it, basically, right?
Yeah, I would put a small paragraph about the theory, explaining this 1 over r squared. Another paragraph describing what it is we did. Another a plot of the data. If it was me, I'd try to curve fit it, or I'd try to compare it to a 1 over r squared curve. And then another paragraph saying, well, why doesn't it match exactly? And it probably isn't going to be too bad. When I did it in my office, I was actually surprised that it was as close to 1 over r squared as it was, since I'm really using kind of a pretty primitive instruments, a source that violates this point source approximation by a long ways. But you still get decent data. You still see that it falls off very rapidly.
It should kind of look like an exponential graph, right?
It should look like a 1 over x squared. Yes, sir.
So, if you need help in Pocatello, who do you want to ask to see out of all the nuclear engineering professors we have here?
Every one of them will help you. Dr. Kuhn, sitting right in the back room, will be more than happy to help you, I'm sure. So any of us are willing to take the time and sit down and explain this to you and help you with it. Are any questions? I guess we're completely out of time.
Due?
I have to make them due next Wednesday, which is the last time that we will have your attention.
And I'm just next door on the 3rd floor. You come over there anytime. I'm usually in my office.